Hello everyone, this is Sir Aris. Today let us talk about special matrices and formulas. We outline in the following table several special matrices which are related to a given matrix A. For example, um, the transpose of A or A transpose in symbol, you have A to the power of T or A tilde, A prime or A T here. Um, The formula is simply we interchange the rows and columns in A. For complex conjugate, a bar or a star or asterisk, we take the complex conjugate of each element. The transpose is also called Hermitian conjugate or Hermitian adjoint or adjoint. It's a dagger. So this here is read as, or it's called dagger. Take the complex conjugate of each element and the transpose. And finally, the inverse of A in symbols is A inverse. We've got this. We have discussed this before. We further list another set of special types of matrices. For example, a real matrix is one where if you take the complex conjugate of each element, you still get the original matrix A. It is symmetric if we transpose as long as A is real, we get the original matrix A. It's skew symmetric or antisymmetric if we transpose. It only gets back A if we write in negative here. Orthogonal if the inverse is equal to the transpose. Pure imaginary as opposed to the real matrix here is pure imaginary if when we take the complex conjugate, we need a negative sign to get the original matrix A. Hermitian if the matrix is equal to its transpose conjugate. Anti-Hermitian if the matrix is equal to negative of its complex or transpose conjugate. Unitary if its inverse equal to the transpose conjugate. And normal if you have A times A dagger equals A dagger times A. Here, A and A dagger would commute. An important notation that we will use here is that when we write product of two matrices AB, the element we call AB, the element ij of that product is ABij. That element is derived by taking the elements of ik elements of A and kj elements of B. We sum over all k, and that gives us this element of the product with index ij. For some matrices, it would be important to make use of the Kronecker delta. It's defined as 1 if the two indices are the same, I equals j, 0 if they are not. For example, if you have the element of the Kronecker delta 1 1 or the 1 1 with 1 1 index, that's equal to 1, but the 1 2 component would be 0, 1 3 would be 0, and so on. Similarly, if you have 2 1, that's 0, but if you have 2 2, that would be 1. And delta 2 3 would be 0, and so on. Delta 3 1 is 0. Delta 3 2 is 0 because the indices are different. Delta 3 3 is 1, and so on. So you can keep on going. In this notation, a unit matrix is one whose elements are the Kronecker delta. And we can write I equals delta ij. So if you have the unit matrix 3 by 3 unit matrix It's 1 0 0 0 1 0 0 0 1. Only the elements in the diagonal are non-zero and they are all equal to 1, just like our definition for Kronecker delta. So this is just an example. Show that for any matrix M and a unit matrix I, the product of I and M is just M. So our notation for product IM of an element ij, we can write this in summation form as sum of k times the ikth component of I and M, or the kjth component of M. Okay, so here this I is just delta, Kronecker delta kj. We can separate this into two parts. Say when k is equal to I, okay, and when k is not equal to I k m k j. Now when k is not equal to I, this k is not equal to I, we get the similar to here, I not equal to j, so that's 0. This one is 0, but when I is always is equal to I, then this is 1. So you have m I j, or I m, or the identity unit matrix I times m is equal to m. Okay. Another example, prove that the associative law for matrix multiplication, so A times BC equals ABC, in compact form we just call it ABC. So let's just prove these two parts to this first relation here. An important product would be BC, if you multiply BC, and suppose we call the elements kj, this can be expanded as to just another variable L, B, K, L, C, L, J. Take note of the position of L. It's is placed right between K and J here, so it's always inside. It's to the right for this left side matrix and to the left for this right side matrix. Now, let's expand this or let's determine the ijth component of this matrix. So A, B, C, ijth component. So if you introduce a variable k, you have A, I, K, and the product matrix BC, K, J. So this would be then K, A, I, K, and here we can expand using this sum of all L, B, K, L, C, L, J. So we write this as sum of K, sum of L, all L, A, I, K, B, K, L, C, L, J. And then we can group this two here, sum over all K, that would be sum of over all L, sum of all K, A, I, K, B, K, L, C, L, J. This is just equal to A product AB and its or product AB, specifically the ILth component. Okay, so if we sum all L, A, B, I, L, C, L, J. So here's our notation again for multiplication of matrices. That would be AB times C, the component or matrix element ij. Okay, or ABC, IJ, ABC. So ABC equals AB times C. Okay, another example. Show that AB transpose equals B transpose times A transpose. So AB transpose, um, let's say the IK matrix element of AB, the product AB, you get the transpose, that would be uh, the product matrix element uh, of AB, but we switch the index. Instead of IK, we get KI. Okay, so if we expand this, this is a matrix element of the product of AB. We expand that. Let's say we introduce an index J. You have A, J, no, K, J, B, J, I. Now, this can be written as a transpose, but we switch the index. Instead of KJ, we have JK. B transpose, instead of JI, we have IJ. And then we further rearrange sum of all J, B, I, J, T, A, J, K, T. And this is now again our notation, where the J and the J's here are in the middle between I and K. So this would then can be written compactly as B transpose, A transpose, multiply the two, and that would here, this term would be the ikth component or matrix element. Ik element. This equal to this, Ik and Ik, so you have AB transpose equals B transpose times A transpose. That is actually a general theorem that the transform of a product of matrices is equal to the product of the transposes, but in reverse order, just like here. A, B, C, D transpose, it's D, C, B, A, and D transpose, C transpose, B transpose, A transpose. The inverse, similarly, of a product is equal to the product of inverses and also in reverse order. One more thing, the trace or spur of a square matrix, this is of a square matrix, the notation is TRA, is written as the sum of the elements on the main diagonal. So for example, the trace of A, we simply get by summing all i's where we have only elements of A on the diagonals. We have I. Okay, we simply sum all elements on the diagonal. So if we have A equals A11, A12, and so on, A21, A22, and so on. So we simply sum the diagonal 1, 1, 2, 2, 3, 3, and so on. Show that the trace ABC is equal to the trace of BCA equals to the trace of CAB, basically making a cyclic permutation ABC, BCA, CAB. Let's see if the trace are similar. To do that, let's expand the trace of ABC. That would be sum of all I, A, B, C, I. Okay, so we can factor out this, or we can group together this AB here. So you have AI, AB being grouped together. That would be, we can make a summation of all J, where we combine AB, you have A, I. Actually, this might be a little bit confusing. So let's sum all J, or actually, I would prefer K first. Okay, so you have A, B, IK times C, KI. Okay, and that would be sum of all I, sum of all K, sum of all J. Let's add J. That would then be, if you expand this, let's say J would be the index of summation. A, I, J, B, J, K, C, K, I. But we can always rearrange. Suppose we want to rearrange such that C, K, I goes first, A, I, J, B, J, K. We can just rearrange the order of our summation. Let's say for here we do J first, I, then K. Doesn't matter actually, but we simply just rearrange. So we can think of it as multiplying the CA, grouping them together, and then that would give us CA. So this um, I and I, actually, it would be better if we do this I first. So we sum this over all I. That would be CAKJ, CAKJ. This one here. This would be BJK. We sum over all J. That would be CAB. Okay, but we're summing all over K. That's simply the trace of CAB. Similarly, let's say we want to do, we want it such that B goes first, JK, CKI, AIJ. So we can sum these two first, sum over all K, and that would be BJI, oh no, not BJI, BCJI. Okay, and then there's JI, this IJ, we sum over all I. That would be BCAJJ. And if you sum over all J, that would be the trace of BCA. Okay, so here, actually here, to make it uniform, let's say we sum I first, sum over all I. So this whole thing, this brace here, it would include the summation here, and then we sum, so that we have KJ, JK. We then sum over all J, and then sum over all K to get the trace. Okay. Final theorem: if H is Hermitian, then U, which is e to the power of IH, is a unitary matrix. So the given is that H is equal to H dagger because it is a Hermitian matrix. Now you want to show that U, which is equal to EIH, for U equals EIH, U inverse equals U dagger. That is, it is a unitary matrix. Since H commutes with itself, basically h times h is equal to h times h, it can be shown uh, that e to the power of ih times e to the power of minus ih is equal to e to the power of ih minus ih, which is e to the power of 0, or the identity matrix. So if you have a matrix, this is u times something gives us 1, or the identity unit matrix, then it means that this something is your inverse. So therefore, u inverse is e to the minus I h. So to find u dagger, we expand u equals e I h in power series. So u is equal to summation over all k of I h to the power of k divided by k factorial. So one important thing that we need to consider here is that the transpose of a sum, say this sum, is just the sum of the transpose. So we can individually take the transpose of each term. Our goal is to get the transpose conjugate. So we have u dagger would be, so we applied the complex conjugate on each term. So you have summation of over all k becomes minus I complex conjugate, and you take the transpose conjugate of h, that's h dagger, k over k factorial. So you have sum of all k minus I. What happens to h dagger? H dagger is equal to h because that's the given. H is Hermitian. The power of k divided by k factorial. This is e minus I h. So it means that u dagger, which is e to the minus I h, is just equal to the u inverse. And this is what we need to show that u is a unitary matrix.